All right, thanks very much first for inviting me. This is actually my third talk this week. It's been a busy week in the talk business.
Wow.
Two ham radio related and one work related. So I get a lot of questions about antennas and what they mean, how they work, and which antenna is best, and things like that. And those are kind of unanswerable questions. But I think, and I hope through this talk, I can give you some guidance about the things that you might want to look out for when you're trying to figure out what kind of an antenna system might work for you. So a lot of you may see antennas as a kind of mysterious thing. How they work is a little bit complicated, actually. If you look at the kind of analysis parameters, you look at trying to run this through Maxwell's equations, it's not easy. Some of the designs you see aren't entirely intuitive. And of course, it's Maxwell's equations, and we're going to touch on it very briefly, but we're not going to go into any depth about this at all. I'll throw some equations on the screen, but don't be scared by them. We're going to gloss over them for the most part. It's for people that want the in-depth. We could go there someday, but not today. So let's try to demystify these antenna things a little bit. We don't have to care about every little thing. We don't have to care about every calculation or optimizing every part of the system. Clearly, there are some things that are more important than others, but what are those things that are more important? And that's what we're going to explore here. You'll see that a lot of antennas are similar to other antennas. They're just some kind of variant in one way or another. But if we know what matters, then we can choose to optimize what matters most. So we're going to start with the basics. We'll look at some simple structures. Then we're going to look at some simple models, and then figure out what we want out of this. And one of the important things we're going to look at is where the power goes, because that's what we really care about, right? You know, the fields are this and that, but we want to know where the power goes, because where the power goes is, well, somebody said too distorted to easily hear. Where the power goes is what really matters. All right, so there's a bunch of calculations you can do about dipoles, and the calculations that we do are usually of a sinusoidal assumption. So we assume that the current varies sinusoidally down the wires going out from the feed point, and we do some calculations based on the free space impedance. And we did this thing called the far field assumption, because the near fields are too twisted up to really understand them without going really deep into calculations. And then we calculate field strength from there. We get this kind of a thing going where you can see that the voltage and the current kind of vary in out of phase from one another like that. And if they're really out of phase in the right way, energy is not going anywhere. They have to be somewhat in phase to actually have power being transferred out. But that's kind of what it looks like, although not entirely accurate. It has a lot of assumptions in it. And then we have to take all this thing and we have to couple it to space-time. We use the wave equations, which are kind of fall out of the Maxwell's equations when you take out all the static parts. And you can calculate these things out and get the free space impedance, for example, or the speed of light and a few other things out of that. And we find out that the space-time has this free space impedance. It's about 120 pi, which is 377 ohms. And the thing about that I was mentioning about the animation earlier is that it has to appear dissipative in order for it to go, for the energy to propagate through space. And dissipative means kind of like a resistor. This is what we're sort of an animation of where the energy goes. It goes out into the fields. Sometimes it goes out into the fields and it comes back. That's not dissipative. That's reactive. And when it actually goes away from the antenna structure and moves out following the wave equation through space and over time, then that looks more resistive. And that's an animation. This is, I believe, the pointing vector, which I'll talk about in a moment, which is a representation of energy motion. And that's for a dipole. And this is kind of what the circuit looks like, an equivalent circuit. You have some kind of generator on the left, and then you have two resistors. One of them is the radiation resistance, and the other one is the loss resistance. And the radiation resistance is that dissipative part I was talking about. So whatever you dissipate by, and it's not turning into heat, it's turning into fields that propagate away from you. That's the stuff we want as radio operators. And then you have this resistor that represents the loss, and you can guess pretty quickly that the ratio of those two resistors is really important, and that in fact defines the efficiency of your antenna system. So if the radiation resistance is really low and the loss resistance is high, well, most of the power is going to go into the loss. But if the radiation resistance is relatively high and the loss is low, most of it's going to go into the propagating fields. So this is a concept that is very useful when you're thinking about an antenna. It's different than the feed point impedance. It's often close to it and similar to it and related, of course, but not the same quantity. Now, speakers, I find this analogy to be really useful. If you think about a speaker, it works kind of the same way. It has radiation and it also has reaction. And if you just had it, let's say you didn't have the cone there, so you weren't pushing against any air, the thing would move back and forth, but no work would be done. And by work, it's a specific thing in physics. Work is kinetic energy by the work energy theorem, and it's conserved in one way or another because it's energy. And it's force times distance, or actually as vectors, it's force F dot D. So it's a dot product of the force and the distance. So if you put the cone back in the speaker, it's going to push against the air, and it's going to have a force, and it's going to push it over a distance. And that's work that it does. And that's the resistive part. It's the part that actually pushes the air around. If you put a speaker in a vacuum, it'll look reactive. And I'll bet you if you take a speaker and put it in a vacuum chamber and you observe the voltage current relation, you'll see it turn reactive, and then put the air back in and you'll see it be resistive. Now here's a bunch of other equations that are probably pretty boring that would kind of tell you what the feed point resistance or the feed point impedances and the radiation resistance for a dipole. These are all based on a lot of assumptions. They're up there for reference. But they give you some calculations you can work with. That's how you get the magic 72 ohms you've probably heard quoted here and there, and 36 for the monopole, and then some short dipole calculations as well. So from that, you can get some sort of rule of thumb equations that help you when you're looking at what your antenna's feed point and radiation resistance will be. Now, I mentioned this earlier, the pointing vector. This is a really interesting thing. It's E cross H, where E is the electric field and H is the magnetic field. And this represents energy flow. And you may think that, for example, if you have a battery like that and a resistor, that the energy is flowing in the wires, right? But it isn't, at least according to this theory. The energy is actually in the fields around them. So you have a magnetic field formed by the wire with current in it, and you have an electric field because of the voltage differentials. And if you do the calculations with E cross H, you'll find out that that all of that energy can be accounted for in the fields, which means that it's not really flowing in the wires, which is a pretty interesting concept. And this works at RF as well, but at DC, you have a pointing vector, and that's how it does work on things. There was this notion a number of years ago, it was really popular maybe 20 years ago, something like that, that we could somehow get this E cross H thing to happen without a conventional antenna. If we could just get the electric field and the magnetic field coerced into the right way, we could make them get a vector cross product, and then we would have an antenna without it being an antenna. But it doesn't quite work that way. We found out every time we tried to put things together, we tried to make them out of leaky inductors and leaky capacitors, but it didn't really work. And what you ended up with was just inductors and capacitors. You'd have this reactive fields and you wouldn't get it to propagate. So we ended up back basically tinkering with these things until they became dipoles again. So there's something very fundamental about the dipole construction. And in every antenna we're talking about, you can find a dipole in there somewhere. Now, how do we get radiation? Well, if you take it all the way back to the charged particle model, you have in that diagram on the right-hand side at the top, you have a charged particle and you have an electric field that results from that charged particle. And that's what Maxwell would say, that it would all be, kind of radiating out, which means it has a del dot charge density propagation. So that the fields are actually coming out. There's a net outflow of fields. And you move that thing, you move that charge, you actually create a little kink field, and that creates.
She looks sort of like what I thought she was looking like.
And so it's all in how we move the charges. If we move the charges, we get this kink that propagates away from where the charge is. And so when we think about that, what is, does anybody know what the technical definition of current is? No takers? dq dt, exactly. So the time rate of change of charge. And so that's like moving these charge carriers or particles and causing these kinks in the fields. So this is a clue as to what's going to be important about radiation.
Oh, pretty good money.
Now, pattern is something we have to consider with antennas as well. So we learned that current's important. Current seems to be mapped onto propagation in some way. But pattern is an important factor too. And when we talk about different antenna structures, including the off-center fed dipole, which was mentioned earlier, we're going to talk about pattern a bit. All antennas are anisotropic. And that's a pretty bold statement, but I think it's pretty true because we live in the real world, not in the ideal world. We talk about idealized isotropic radiators, which means they radiate the same in all directions, but nobody can build one of those because we have finite sizes of things. So they do have preferred directions, and it depends on what the structure looks like as to what the preferred direction is. And if we take any kind of antenna structure and then we say, well, what's the power ratio at a certain point away from the antenna, say the ratio of power like right nearby the actual metal and farther out, you'll see that the three-dimensional surface comes out from that. And that three-dimensional surface that forms when you do that is called a pattern. And that tells us where the energy is mostly going for a particular antenna structure. There's two slices of this pattern that we tend to look at. We take a slice through that 3D surface. If we slice it horizontally, we get what's called the azimuth pattern. And that's as if you're looking down on the antenna. How does it rotate, or I'm sorry, how does the pattern vary as we go around in a circle, looking down from the sky into that horizontal slice? And then there's the elevation pattern, and that is slicing it vertically. So we have this 3D structure that I was talking about earlier, and we slice it vertically in view from the side, and then we can see how the pattern, how the energy varies from top to bottom. And, that translates often into an angle to the horizon because we have something kind of pointed at the horizon, and you'll see where most of the energy goes. It doesn't go in any particular direction. It kind of goes in all directions, but to a varying degree. And that varying degree is what we're really interested in. Now we have this notion of effective radiated power. And you can think of this as a focusing lens. So if we have an isotropic antenna, we just have the power going everywhere. So you can just say, well, it's this big sphere. And that's easy to think about. But as I mentioned earlier, antennas are anisotropic. So we have a peak area. If we look around, some things don't have a peak like this particular pattern. But if we can find a peak, we can say, what's the ratio of the power at the peak to, say, the power we put in? And that will tell us what the effective radiated power is. And if the antenna has a very narrow pattern, it's concentrated, like a lens might do. So you can think of it that way. And this one very clearly has a peak. And so you can say, well, the ERP in that peak area is going to be much more than it would be if it were spread out. And that's why when you have, for example, one of these really small 1.2 gigahertz 12 element Yagis, you probably don't want to be looking into that very much because it might cook your corneas because it has a lot of ERP, a lot of large effective radiated power. Now, terrain, of course, affects pattern. This is something we always have to deal with. It has a very complicated relationship because the terrain is not a stable medium. It has wetness. It has ionic compounds like salts in it. There is the individual constituents of the dirt, which can vary from place to place. We have all these angles because we have structures that are not flat. So we have refractions of different kinds, and then we have the height of the antenna itself. And the polarization, that also matters, and we're going to talk about that in a sec. But you can see this is kind of a hard graph to read, but this is showing, I believe, on the y-axis is the angle that a signal might come in given a certain terrain. This is a program that was who wrote this program? The guy who used to edit the antenna book, right? Dean Straw, that's right, for analyzing these situations. And here's a simple example of a difference. This is a repeater pattern. And this is at 440, and you can see where the repeater is with the little flag. And then if you go to 2 meters, well, it's quite radically different. So it's frequency dependent as well. So there's all these dependencies, and it'll rain and it'll change. So, but the best you can do is kind of look at what is most of the time where you live and try to work with that. Polarization, as I mentioned, is really important. If we have things that are horizontally polarized, we tend to have what's called image currents in the dirt. And the image currents in the dirt are actually kind of reverse of each other. And what they have a tendency to do is kind of cancel out closer to the dirt. And the higher you get, the more they kind of enhance. And the canceling and the enhancing is kind of like additive and subtractive. There's no energy lost except the part that heats the dirt. But for the most part, in this effect, it's pushing the pattern up by concentrating it up at a higher elevation. And so when you get closer to the surface of the earth, those image currents are closer to one another, and that causes the pattern to shift up. And that's mostly by, destructive interference and constructive interference at the top. So it also depends on the dirt itself, but as a general rule, you can think of this magnetic field component of a horizontally polarized antenna causing this pattern shift. So if you have a low horizontal antenna, chances are you're not going to have a pattern that's low to the horizon. Now, we're all DXers, right? That's not what we want. We want that low horizon pattern. And this is a low horizontal antenna is not going to get that for you so easily. Now, vertical is different. We have image charges as the dominant effect. In this case, the electric field component. And those tend to pull at each other. They attract one another. And so the pattern actually gets pulled down towards the surface of the earth. So often there's a null at the top if it's just a vertical. And it will actually, if you have a better conducting surface, like you've heard about the salt water effect, as you get close to the salt water, you get better image charge effects. And that tends to, by constructive and destructive interference, pull that pattern down. So that's the consideration about what you want out of the pattern. If you're trying to do NVIS, this is probably not a good plan to keep it low. But on the other hand, if you were doing horizontal on NVIS, it tends to work. So if we go back to dipoles and take a look at them, they have an interesting pattern all in their own. And this is what it looks like in free space. It's a donut or a toroid, as we call it. And this is actually better than an isotropic radiator because you get a certain amount of concentration and you get nulling along the axis of the wires. And this can be really good. It's 2.2 decibels above an isotropic radiator. So that's really good. But again, it's affected by polarization. So a vertical dipole versus a horizontal dipole is going to give you a different outcome. And it's not an outcome that's based too much on loss. It's mostly based on these image charges and image currents. Dipoles are nice in that they have a fairly high radiation resistance. It's close to the feed point impedance, so 70-ish ohms. And if you make them fatter, they tend to have an even higher radiation resistance. And they're really easy to feed. especially if they're horizontal. If they're vertical, it's a little more of a challenge, but not impossible to do. Vertical dipoles perform very well. But they're nice antennas and they're very simple. It's the most basic antenna structure that there is. And this is what it looks like sliced in the different planes. You can kind of see the vertical slice on the bottom right, and you can see the horizontal slice on the bottom left. And you can see that it's very symmetric from if this is for a vertical dipole, very symmetric for the azimuth. And then an elevation pattern is just like the donut, just sliced. So what matters here? We talked about a couple different antenna things. Well, the things that I think matter about this and trying to make an antenna that's going to be functional and useful for you is a simple structure. You have to be able to put this thing up, remember? That can be a real pain depending upon where you live and what you're doing, whether it's permanent or not. Pattern is really important. So it depends on the dirt and it depends on the gain in different directions. And this is something that I think
You can put that on.
especially when we deal with sort of multi-band antennas. This pattern shift becomes very interesting because this pattern will vary with the frequency. We want to minimize loss, which means we want a fairly high radiation resistance, as high as we can get it. And we want to be able to couple it to the transmitter. Remember that what we're trying to do with the transmitter.
Oh, true.
Transmitters that we build in ham radio are really happy when they're feeding a 50 ohm load. And if you want to make your transmitter happy, you coerce whatever you're driving into 50 ohm resistive, and then the transmitter will be very happy. It's not a matter of energy transfer. There's a lot of incorrect thinking, in my opinion, around things like the maximum power transfer theorem. I have another talk where I dip into that one, but that has a certain assumption that's not true when we think about things like this. The thing you really want to worry about is just making the transmitter not get hot and be happy to drive that load. So now we come to this thing I was talking about with patterns and elevation. And the question is, what do you want to do with this thing? And that's what you can't lose sight of. So our goal in ham radio is station-to-station communications of some type. We're trying to create a circuit, evanescent though it might be. And in the case of VHF, it's kind of line of sight for the most part. You know, we just kind of point the antenna where we want it to go. But in HF, it gets more complicated because we have this refractive property of the ionosphere. So the angle at which we launch our RF energy starts to really matter. And that angle matters for a couple of reasons. The dominant ones are if the angle is too large of an angle to the ionosphere, the energy will not refract. It'll simply go out into space so you can talk to the aliens. That's what you're after, go for it. But if we actually want to talk to the DX, we got to lower that a little bit. And as we lower it, it's going to change how it refracts in subsequent jumps like that. And that amount of refraction is frequency dependent as well as dependent on the charge in the ionosphere. So we have to think about where we want that angle to be and how much directionality we want. If we're trying to work a specific DX station, we probably want a lot of directionality. If we're operating a contest and we're on the West Coast, we want it front to back ratio. We want to push it in one direction, not the other, perhaps. If we're in the center of the US and we're operating in North American contest, we want it omnidirectional. It depends on what you want. And you can see here that you get different patterns depending upon the polarization. And this is an example of a quad. And let's see if I get the colors right here. I think the blue one, you can see there's blue and black. And I think the blue one is vertically polarized on the quad. And the black one is horizontally polarized. And this is the same antenna. Is it the other way around? Okay.
The other way around.
And it's the same antenna at the same height. So you can, over the same terrain. So you can kind of get the same idea of just how changing the polarization changes the pattern. It's pretty dramatic, as you can see. And it might be advantageous to have the blue one or the black one. Depends on what you want to do. Now, there's this other parameter that we often don't talk about in ham radio, and that's aperture. Aperture is kind of like gain. Just wanted to let you be aware of it, just if it ever comes up. occasionally it does in ham radio. Usually in non-ham radio context, people talk about apertures and antennas. It's kind of like the opening on a telescope or something like that. How much of that light, which is in this case is RF energy, can get in through that opening. It's you can think of a wavefront as an expanding sphere, and you're trying to capture a chunk of that expanding sphere into your antenna and figure out what the power flux is through that opening. And so you get a few equations around that that can help you calculate things. The most interesting one out of all that is what's called the Friis transmission equation. That's a really useful equation if you're trying to build a contest station with multiple operators. So when we were operating the California QSO party, or field day, trying to cram a bunch of stations, which we mostly did at Cal QSO party, that was the most challenging operation, where at one year we had 5 people in a multi-op and a single op. I was the single op, and we were all operating same band, same modes on and off. And it was tough, but the way we got it to work, other than good filtering, was this Friis transmission equation, which told us how much isolation we could get for how much distance given the antenna gain in that direction. So that's a useful one to know, and it depends on the apertures. Now Q, I'm sure you've heard about Q. It's sort of a measure of how wideband your antenna is. In this particular case, there's an interesting thing about Q, and that's called the Chu-Harrington limit. Some people dispute whether that's actually the limit or if it's something more constrained than that. It's not a theorem. It's not something we can prove exactly, but what it says is it gives us some guidelines to work with, and it has to do with a sphere that encloses the antenna structure. And the smaller that sphere is, the smaller the radius of that sphere is, the higher the Q will be of the antenna. And that means it gets narrow banded. So if you have, for example, one of these so-called magnetic loops where you have to tune the thing, you'll find that the smaller it is relative to the wavelength, the more narrow banded it is, to the point where at some point you can't even modulate it. So that's something you have to be aware of. You can shrink an antenna structure to a point, but at some point it becomes not a useful antenna anymore. Now, loss, we haven't talked too much about loss, just briefly, but this is an important thing to worry about too. And I categorize it in these 4 ways. You're either heating the dirt, you're heating some wire, you're heating a coil, which is sort of like heating wire, or you're heating the feed line. But almost all of the loss gets lost to heat. And so what you see here is that, you can minimize that loss by maybe using the right kind of wire in the right way, but, or putting a lot of radials out, that helps too. But this is the way you don't minimize it. And you may have seen this on some QRP antennas where they have a little shorting wire on the coil. And so you use this to kind of tune the antenna by changing that inductance. And you can think of that as sort of lengthening or shortening the antenna electrically. But does anybody know what the problem with this is?
Couple currents.
Yeah, circulating currents, exactly. So the current is going to circulate around that coil and that shorting wire, and it's going to warm it up. And that's not what you want. And so more ideally, you'd want to break that circuit and not have it be connected like that in a loop, or you can put a shield over it. The super antennas, anybody remember that? MP1 and stuff like that? That antenna has a shield over it. And so it's quite efficient because it covers up electrically that other half of the coil. And so it's not subject to these circulating currents. So I have arrangements where I either use a fixed coil or I can disconnect it so that we don't get that circulating current problem. So with all of this, we have some values for ham radio, right? What we really want to do is talk to another station. We'd like to have a stronger signal if we can do that, right? That's more fun. We want to have a reasonable structure that we can deal with, because we have to actually build these things and deploy them, and maybe even deploy them permanently, who knows? And then an easy interface. And by that, I mean, can the radio talk to the antenna with minimal losses? You can always put a tuner on there, but how good is the tuner? And how much are you losing in the coax as a result of that? So from those values, we get some principles. We want to optimize the pattern, and this depends on what you want to do. As I mentioned earlier, are you into DXing? Are you into contesting? Is NVIS your thing? Do you want omnidirectional? You're running a net? All this stuff matters. We generally want to increase the radiation resistance so that we have, kind of lower proportional loss resistance in other parts of the system. We want to choose our aperture or gain in a way that makes sense for what we're doing. If you're contesting, a very narrow antenna is not your friend. It's actually your enemy. But in DXing, it is your friend. And then, what's the structure that's reasonable for you? Is it going to be something you're going to make yourself, something you're going to buy? How big is it? How high is it? If you don't have access to high things, maybe vertical antenna works well for you. It's something you have to think about. So what this gives us is a lens, and we can look at what we're building and what we want to buy, or whatever we end up doing, by looking through that lens and look at each antenna structure we're interested in and see how it kind of stacks up. What do you lose? What do you win on? There are some structures that may be perfect for one person and horrible for another. And the thing to keep in mind, though, is that the perfect antenna does not exist. You're going to make a compromise. It's a question of which compromise and how. Some people have optimized very highly, and they're usually in a perfect location on a, maybe on a hillside or something like that, going in the direction that they want. But the perfect antenna is just not there, so don't bother looking for it. Although, tweak till you get it as close as you want, but don't stress over it. Now, while we're here, let's talk briefly about SWR. Some people really stress over SWR. I have a whole talk about that. Do we really care about this? Well, not really. It's not such a big deal. We're trying to make our transmitter happy. And if the transmitter's not happy, all the power that it could possibly deliver from the power supply out to the coax is not going to happen. So we do have to worry about that. The coax efficiency generally doesn't matter that much at HF. If you actually do the loss equations, run the loss calculations, you'll see it's not that bad, even with pretty high SWR. It's usually, a dB or two. That may be very important. Again, it depends on what you're after. But the thing about SWR is that it doesn't tell you everything. I call it a degenerate metric. And if you look at a 3-to-1 SWR, as the example shows there, there's an infinite number of solutions to 3-to-1 SWR. And two of them are 150 ohms and 16 ohms. That's pretty dramatically different. So when you see a 3-to-1 SWR, you can't tell whether it's that 150 or 16 or any number of other reactive solutions to that. So it doesn't really tell you that much. And as we always say, a 50 ohm resistor matches perfectly. And that's what this is evidence of. It doesn't tell you like what the power transfer is into space-time. So it's kind of one of these things where you're trying to look at what the match is so that you can get the transmitter happy and think about your coax loss. But there's not a whole lot more to it after that. I mean, I remember one really fun time when I was in Anaheim for a conference, and I was on the roof of a parking garage and there was nobody else there. So I spread out my radials and my short vertical. And usually that thing tunes up very nicely, but it coupled into the rebar, I believe, in the parking structure. And so the SWR was like 3.5, 4-to-1 or something like that. And I heard Victor 55 Victor on there, and I really wanted to work Victor 55 Victor. And my stupid K2 would just fold over. And so what did I do? I turned the power down. I turned it down to about 50 watts, and guess what? Worked great. I worked them. So I made the transmitter happy enough to get half of the power I wanted, but that was enough. So we're going to go through now a few examples of antennas that we can look at and kind of see how they stack up, and maybe that'll give you some ideas about what you want to do. You can see the list there, and well, let's just dive in and talk about some of them. So this is a monopole. I use this for operating in the field a lot. It sort of has a radiation resistance around 36 ohms. It depends very much on what the radial field looks like. It has a 5 dB gain-ish over an isotropic structure. And so that's good. It tends to have a fairly low launch angle. That's good, right? So that means it doesn't have to be up high, but it's kind of low. If you see a low Q, watch out, you've got a lot of loss going on. You'll see that some people will couple into these things that give you like 4 radials, right? And then you hook it up to your transmitter and you notice the SWR is great. It's 1-to-1. Well, why is that? Well, it's far away from 36 ohms. It's more like 50 ohms at the feed point. And so, you're just heating the dirt, and that's not helpful. So if you have one of these antennas and you like using them, I start with 16 radials and I go up from there to about 39 or something like that. After that, it's diminishing returns, but you'd be amazed how well an antenna like this performs if you have more radials. And if you raise the coil up, that really helps too. So when I have an antenna like this, the first thing I do is I buy more lower sections and I push that coil up into the air. And that gets more of the current, the radiating part of the antenna, available for you. And this is the shortened monopoles, shortened dipoles with the coil. I just kind of talked about that. They'll have this lower resistance, usually at the feed point, lower radiation resistance for sure. And that means more potential for loss. So if you have an 80-meter antenna that's this tall, I don't think it's going to work too well for you. I don't expect it to. You really want some good radials if you're going to try something like that. But you don't need any height. And the Q will depend very much on the losses in the system. And you get the pattern concentrated in the high current section of this antenna, which is going to be the part closest to the feed line, between the feed line and the coil, basically. That's where most of the energy is going to get out into space-time. So that's what you want to maximize. If you can make that section longer, you'll have a higher radiation resistance, and that'll be a win for you. But, caution, like this here, you can see this antenna with the little capacity hats is horizontal. It's sort of like a buddy pole, but with capacity hats. And those things don't work well close to the ground. So a lot of people that buy a buddy pole put it close to the ground horizontally, and they're a little bit disappointed with the performance, and that's why. If you're going to be close to the ground, make it vertical. If you're at the top of a mountain, then horizontal may work very well because you're not going to have that effect of the image currents. Horizontal Yagi, we're all familiar with this. This is a great antenna. It has a narrow aperture potentially, depending upon the boom length, more than the number of elements. The boom length really matters. It will have a kind of a low radiation resistance. It depends very much on the structure. You'll note that the feed point impedance is usually in the tens of ohms, like 14 ohms or something on that order, and that we use a match to try and fix that. But the point is that if you have any resistance in there, that's not going to be good. So we use good metals that are good conductors, like aluminum is a fairly good conductor. And you get a very directional pattern out of this, and you get fairly good front to back ratio, but it all depends on the element spacing and stuff. But it's a great antenna. The problem is if it gets big, how do you get it up there? If you have a tower, good for you. They can be heavy too. So that's a consideration, but you can get a very narrow pattern out of these things, as I'm sure you know. Now, here's one of my favorites to talk about, the G5RV. This is everybody's solution, especially when they start out. But the thing with the G5RV is, it kind of matches, but it's all over the place. It's just not anti-resonant where you want it, which means your transmitter will sort of be happy, and your matching network, aka tuner, will probably match it. But you can see from these pictures that the pattern is all over the place. And it can get really spiky and weird at times. And so, it matches. Yeah, you can drive it. Yeah, you hear signals and work people, but it's not optimal in many cases because a lot of the energy that you're, say, facing Europe, some of that energy is going up into the poles and through the auroral circle and not helping you at all. So what fraction is going to Europe? Some, but maybe not all that you think. You switch bands and it's all different again. So it's not a clear pattern. 20 meters, it tends to have sort of a dipole-ish pattern, but other places it's all over the place. Large loops are nice if you get them. They tend to want to operate at a particular frequency. They have a fairly high radiation resistance, which means they can be quite efficient. The amount of height required, of course, depends on the polarization, like I said before. vertically polarized, close to the ground tends to work well for low angle radiation and vice versa. And they have this, big bulby toroidal pattern, which could be very useful. It's nice, you got a couple of nulls you can play with. They're kind of like dipoles that are folded over one another. Now here's a small magnetic loop. These are fun antennas. I have a couple, and I've made a couple, and they're very tiny. But the thing with these antennas is they have a very low radiation resistance. It can be in a hundredth of an ohm or lower, about down to a thousandth of an ohm. And this is why coupling these things is really hard. If you really want to couple it, you have maybe a loop of copper or aluminum is a little worse. But copper and then coupling that into the capacitor that you tune it with can be very problematic. And you probably want to silver solder it because you need the resistance to be that low. And, for that antenna there, that's the, what is that called? The Alex loop. Poor Alex just passed away recently, didn't he? But I have one of those. And the resistance of those PL259s there can be an issue. And he did provide plated ones, so it's not as bad as the usual sort of tin plated ones. And these are super high Q. If you've ever played with one, you can just get a slice of the band, you move down the band, you got to retune the thing. But that's the way it works, and this is what the Chu-Harrington limit would predict. The sphere that you enclose this antenna with is very small relative to the wavelength, and so the Q is going to be very high. And there's been some fun work that's been done with automatically tuning these things as you tune the transceiver. So it's not as much of a restriction as you might think, but still, there's going to be very high fields near these things, very high field density. It'll cook the paint off your walls sometimes. And, you've got this capacitor with very high voltage on it. And that radiation resistance will kill you if you don't get it well connected. Half-wave end-fed. What's another name for a halfway end-fed? Dipole. It looks a lot like a dipole. The problem is that you're feeding it from the end, which means you have a fairly high voltage developing there. The easy way to get that to happen is with a transformer, because transformers transform voltage and current, so you can trade off and get high voltage and low current. The problem, of course, is that node is very sensitive at that point. Any structure nearby is going to drag it down if you're not careful. How you kind of connect the other end of this is an interesting problem, because there's no such thing as one wire being a circuit. There's always a second wire somewhere, one way or the other, that's going to couple to the field. So there's got to be another radiator somewhere. They show a ground symbol there. I don't believe that works too well. I mean, if you can couple it to the dirt, it'll kind of work, but there's certain loss here. And if you've ever seen my talk called Ground is a Myth, you'll know that I don't like to use that word. But again, these are just like dipoles, so they have the same restrictions. If you really want a low pattern, you got to get them up high. They do work, and in some cases work well. The ARL sells the half-wave end-fed for 40 meters, and people have had a lot of fun with that antenna, and that's great. But you have to realize the constraints on this antenna. Now here's the off-center fed dipole, and I don't want to upset Tony here, but it's another dipole. There's not too much difference. It's just that it has a funny feed point impedance. So you're sliding that thing. It's like a G5RV. So you're sliding the feed point over, and you're getting a different feed point impedance, usually more reactive. And in that case, you can avoid some of the anti-resonant points, sort of like the G5RV does with its transmission line transformer. And you have the Balun losses that go with the matching and that sort of stuff. But there's no magic here. This is sort of like a doublet more accurately than a dipole. I guess that's what we call dipoles that are not operating at the frequency that matches their length. I don't know if that's a reasonable term for that, but that's what people seem to use. And so you really don't have anything magic going on here, sort of like the end-fed half-wave. It's another dipole. J-pole, this is a really interesting antenna. These are hard to analyze. This, you can see from the pattern that it gives you a slightly elevated pattern, which makes it really good for doing omnidirectional VHF work because it's small enough. Although people make them for 6 meters, even 20 meters I've heard of. And this is another form of an end-fed half-wave dipole. See, a lot of these antenna structures are the same. And in this case, we have a transmission line transformer at the bottom. And well, you can see the short part, right? So that defines a boundary condition. So it's 0 ohms down there. And then we move up a little bit for the given wavelength, and we find out that we can find sort of the 50 ohm point-ish. It might be slightly reactive, but that's okay. And then the impedance continues to transform as we go up that transmission line transformer until we get to what looks like kind of an open circuit-ish thing, which is what we want to feed a half-wave dipole. And the looping back part at the top, that's just sort of a folded dipole, slightly changing the impedance and changing thus the calculations. But again, it's a lot like an end-fed half wave. And you have this matching section. But the interesting thing about it is that it's out in the open. And so the fields interact between the half-wave dipole part and the transmission line transform. So they influence one another, and that helps favorably push the pattern up even more. So it's an interesting antenna. They're easy to build. I think I'm going to be helping put together something for Palo Alto, the Para. They're going to do a Para in the Park event, and we're going to build 300 ohm twin lead dipole or J-poles. It'll be a fun project. And then there's the isotron. Anybody have one of these? No. Okay. The claim with the isotron is that we're doing pointing synthesis. We talked about that earlier, where we get the magnetic and electric fields to cross each other just right, but it doesn't work. It's just a load on top of a piece of coax, and the thing that's really radiating is the outer shield of the coax. So it's just a reactive terminator on the end. It doesn't really fit with our principles. So I would say avoid this particular device. So going back and thinking about what we've talked about, what matters most, we want to communicate, right? And the pattern is really important for that. We want an efficient system because we don't want to, heat up too many things because that's a waste of power. And so we have to worry about the loss resistance and the radiation resistance and the gain of the antenna to get it the energy pointing in the right direction or no direction, if that's what we want. And then we have to think about how convenient is it to deploy this antenna. That can be a real factor in how you decide what you want to do. And then there's the transmission part, which is the feed point impedance, not the radiation resistance. This is how you make your transmitter a happy camper. You want to learn more about all this stuff? The Aero Antenna book is a great reference, even if you have a really old one like the one I have there. That's actually a picture of my antenna book. And also, there's a lot on Wikipedia, which tends to be kind of obtuse. So if you want to dive into the math, that's one way to do it. It's not very deep. Or you can pick up an antenna theory book. That's the one I have that I happen to pick up at a flea market. That's an okay one. Or you can get one of the more classic texts. And use some common sense about, and I'm not meaning to yell at anybody, but look at these principles and then just apply them and think about what matters most. I'll take questions. Yeah.
I have a question about, talk about radials for a minute. Just with regard to 40 meters, because I know it's going to depend on what Japan doing. But 40 meter radius, how many length, at what point do you have diminished returns?
Okay, so the question was 40 meter and radials, how many length? Let me ask a question and then I'll answer. On the ground or elevated?
Using the little an elevated coil.
An elevated coil. Okay, so the radials are up a little bit off the ground, as you're saying.
Well, right now they're not getting.
Okay.
So like the coil.
Well, let me give you both answers and then you can choose. Okay, so let's start with elevated. Calculations and demonstrations have been done that show that you can get away with as little as 2 radials if they're tuned and above the ground, where above the ground is probably a couple of feet, maybe 6 feet off the ground at a minimum. And that most of the energy is not going into the dirt at that point. And those have to be tuned to the length, to the frequency of operation. If they're on the dirt, they're going to be detuned anyway. So the length doesn't matter as much. A minimum of a quarter wavelength, I would say, somewhere between a quarter and a half is adequate. Yeah, all the same length, unless you want the pattern to go one way or the other. That's another thing. But if you want an omnidirectional pattern, you want them all the same length. And A minimum of 16, 40 meters. Yeah. It's a minimum of 16. And then when you get to above 30, it's starting to diminish, but not 4. Other questions?
Any questions on Zoom?
Have you ever used?
No. I'm good.
Yeah. I can tell you about that.
Yeah, it was a great talk.
Oh, glad you enjoyed it. Let me answer the Faraday thing. I've used Faraday cloth at work, believe it or not, and people think it works, but it doesn't.
I rang once.
It's not, even at microwave frequencies. It's no good.
He got the message the first time, but I couldn't really understand it.
Well, it works, but it doesn't seal, so it doesn't actually create a Faraday shield. So people wrap it around stuff. And
They use them in South Korea.
That was
Wrap around
before
ladies that are, using it as like 9 months pregnant.
using it in place of radials, yeah, that might work. As long as it can conduct amongst itself and doesn't oxidize.
Grounded to Faraday.
Yeah. But as using it as a Faraday box, no, it leaks too much. Any other questions?
Good talk. Good talk.
All right, thank you.
Thank you.
That was a great discussion. Thank you so much.